All right, so in the next few videos, we're going to be doing practice problems related to a lot of concepts in Chapter 8 and Chapter 9, Lewis structures and VSEPR, the shapes of molecules. So for each of the following molecules, we're going to start off with a simple one, H2. We're going to give the Lewis structure. We're asked for the steric geometry, the molecular geometry, and the bond angles. Okay. So this first one is hydrogen. So first thing we need is the number of valence electrons. Well, hydrogen is number 1 on the periodic table, has 1 electron, 1 valence electron, right? And there's 2 of them, so that's going to get us 2 valence electrons. And so we can write our skeletal structure. We're going to connect them by a bond. We know there's 2 electrons on bond, and hydrogen follows the duet rule. It wants 2 electrons. It doesn't follow the octet rule. It wants to be like helium. And so this is the Lewis structure. Steric geometry. Well, there's no real central atom here. So this has to be a line, right? And so both of these, molecular and steric geometry, are going to be linear, right? There's just 2 points have to make a line. There's nothing else they can make. And the bond angle of any line is 180 degrees exactly. Next one, fluorine, 2, very similar. Different number of valence electrons. Fluorine's a halogen, so there's 7 valence electrons for that. There's 2 of them, that takes you to 14 valence electrons. Again, there's only 2 atoms, so that's going to be a line. We're going to have to bond those together. Now we're going to have to satisfy the octet rule. So we're going to put 6 electrons on each, so that in total they follow the octet rule. 2, 4, 6, 8. Right, 2, 4, 6, 8. There's 2 each. You count 2 for each of those fluorines. And how many electrons total? 2, 4, 6, 8, 10, 12, 14. So we're good. And again, this is going to be linear for both the molecular and steric geometries. And the bond angle there, since it's a line, it's going to be 180 degrees. HBr, another linear one you can see, but we're just practicing mostly our Lewis structures on these first ones. Valence electrons. Well, we have 1 for hydrogen and 7 for bromine. That's a halogen. That gets us 8. Put our skeletal structure, connect them, and then we're going to say, okay, hydrogen has satisfied the duet rule. There's 2 electrons there from that bond, and we're going to have to satisfy the octet rule for Br, 2, 4, 6, 8. And let's just count our total number of electrons are also 2, 4, 6, 8. So we're good. And again, this one's not very exciting. It's linear and 180 degrees. Something a little more interesting, let's go to NH3. Again, valence electrons, nitrogen's in group 5. So that's 5 valence electrons. There's 3 hydrogens, each good for 1. That gets us 8 valence electrons. Nitrogen is going to be our central atom. Hydrogen can never be in the center because it can't bond to more than one thing. So we're going to have a skeletal structure that looks like this to start out, right? And now we have to look at, okay, hydrogens are good. They have the duet rule. They have 2 electrons each. Now we have to look at nitrogen. Nitrogen only has 6 electrons, right? 2, 4, 6. It wants 8, so we're going to add a lone pair. And that makes nitrogen happy, and it makes the whole molecule happy with 8 electrons total, 2, 4, 6, 8. Now, so that's our Lewis structure. What is our steric number? Steric number is, remember, it's the number of bonding sites. So we have here 1 bonding site, 2 bonding sites, 3 bonding sites, plus the number of lone pairs, and we have 1 lone pair. So that's going to give us a steric number of 4. That tells us we have a tetrahedral geometry. Okay, and that's the steric geometry, right? Steric geometry. What we're really interested in is the shape of the molecule, which we also call the molecular geometry. Okay. And that's now a tetrahedron shape, but with one of the sides of the tetrahedron removed because there's a lone pair there. And so what that's going to look like is it's going to look like something like this, where you have, remember this is, I don't expect you to know this notation, but this is just to help us visualize this, where you have sort of a tripod, right? And so, actually I didn't draw that the best way. Let me erase that. You have sort of a tripod. Here we go. Tripod type molecule. Okay, so you have a lone pair up here, but really this is a tripod. Okay, and so now what would the bond angle be? Here I can draw the lone pair. Well, for an idealized tetrahedron, it's 109.5. Okay, but we have a lone pair. We know that VSEPR theory tells us that lone pairs have more repulsion. There's electron-electron repulsion, so they take up more space. That's the thing to remember. Lone pairs in this theory take up more space. And so whatever this angle is going to be, both of these, all right, it's going to be less than 109.5. So the bond angle there is something we don't know exactly. We can't know from this theory, but we know it's going to be less than the idealized bond angle for a tetrahedron, which is 109.5. So it's going to be less than that.